Alright, BAS Center members, what we're going to deal with is programming this entire thermostat from ground zero and up using the BAS emulator. So first and foremost, let's open up this emulator and let's create our fake controller, more or less. That's going to do what? That fake controller is going to populate our local host, that 127.0.0.1 address that you see right here. And what it's going to do is pretend for the Sedona application so that we can actually program into it and create our own backup. So one of the things you see up here is 3.1.2 BAS 20. The most recent version, what you'll be using is the BAS 22. So I'd like you to go to 3.127-BASC 22 and click Start Emulator. As the emulator begins to run, we can see our system status. We do not have auto refresh on. We keep auto refresh off for what? Keeping it off until we actually want to just operate and watch our controls, move up or down, right? So temperature sensors, whatever we're watching here. So let's click down here and let's open up the Sedona application. Remember, our IP is 127.0.0.1. You can either hit this button, Open Connection, or you can go to File, Open Connection. I've already got it set. It'll either be at 192.168.92.68, which is what you would choose if you were hooking into a controller. In this case, we're hooking into an emulator. So 127.0.0.1. Remember to type in the password, ADMIN. Admin. It's the top secret password for the whole company. Okay, so here we are on the main screen. Remember again, we see a tree here, which is just something to quickly navigate through. We won't be in the service, but we will be in the sheets. We also have our different I/O and other things over here on this edge. If you guys are paying attention and looking at the screen when I'm talking to you, I hope I'm not wasting my time talking to you and you're paying attention. On the top right, we'll see property and values, and we'll get into that as we start moving further into this project. So we will go into sheets, and one of the first things as we get into the sheets, we want to organize your thoughts. This is going to be really important when you start to work with your students. Organizing your thoughts and getting them to understand how to navigate between sheets so that you can take chunks of logical progressions of control, and you can deal with how that works in your students' minds. It's very difficult in a controls arena to just digest the creation of a monster that a student might have with wires running everywhere. So heed thy warning. So under the Systems folder, see my arrow, follow my arrow down here. Under the Systems folder, we have a folder, and I would like to plop down a couple of folders. 1, 2, 3. Sounds good. 2, 3. 3 folders for now sounds great. So, on these folders, as I was talking earlier, over here to the right, this folder we really don't want to call folder. Let's call it sensors. When I hit enter, the name changes. Let's go down to folder 1. Let's change that folder 1 to control. Go down to folder 2 here, and let's change this to -O. And it tells me no. Okay. Can't have any fancy characters in there. So, this is our baseline where we want to start from. And I want you to understand that you need to have some type of method to your madness, or you're not going to be able to control how your students' thoughts wander, which basically means you're going to have a hard time trying to understand how to digest all this stuff. So, under sensors, we're going to go through what and why, but in the sensors folder, I wanted us to go in and start saying, okay, well, let's close this out here, and let's go into what's CC Controls BAS 22 IO, and we need to have some inputs. So you should now already have your universal inputs. In your universal inputs, we're going to pretend that we're putting our temperature sensors there. Considering this is an emulator, if it wasn't the emulator, you could use this same program and wire up your temperature sensors to universal input port 1 on the controller. So let's go to UI 1 and let's go to UI 2. And we want to take these two controllers, or two inputs I should say, and we want to drag and drop them onto the screen. So as you take a look at it, there's a lot of different information. On here, universal input 1, I kind of like the UI 1, and then I will just put temp up. Just to designate that we are using temperature. Now, what I'd like you to understand is that I'm putting universal input 1 and 2 as temp. I want you to understand that these, currently the channel type is input 10 volts. So the only way to change these are to go to the screen that populated the second we started the emulator. Okay, so if we go up here, we say BAS control 22. Take those out. And I will go into universal input 1. And notice how it says analog input, right? I'm going to change this to a 10K T2. You should have either a T2 or a T3 thermistor that was given to you at the workshop. So I'm just going to kind of stick to what we did at the workshop, and we will go through it that way. Alright, here's where we will put an offset. This is if you don't believe your sensor and you feel that it's failing or reading the wrong way, and the room is 70 degrees and your sensor is reading 72, here's where you can offset it -2. Or if the temperature in the room is 70 degrees and your sensor is reading 68, we add 2. So this offset is where we can add or subtract the offset that exists in your sensor from reading the true actual space temperature. And in units, we would take units down and pick, let's go down to Fahrenheit, degrees Fahrenheit. I like that one. Degrees Fahrenheit. Now, notice how I rolled over. Universal input 1 is there. What I want to do, just for this sake, is on the emulator, let's just lie to this. Let's say 78. We click outside of that. So this is going to be 78 degrees. So this is our way of checking this box and saying, well, right now I want this to be 78. And if you go back down to your Sedona editor, you can see we are at 78 degrees right here. Kind of feel like Bob Ross right now, you know, talking about the trees and the flowers. Look at this wonderful little temp sensor here. Okay, so let's go and change universal input 2, and I'd like to put a 20K. So we're going to go to thermistor 20K. So you were given a 10K T2, I believe, and a 20K at the workshop. So we'll go down, change this again, degrees Fahrenheit, and we will hit submit. I'm just going to close that out, and I will also put, I'm going to put 75. Why? Well, I want our math to make sense. So here right now we see universal input 1 and 2. What I forgot? Forgot to change the name. Universal input 1, let's say temp upstairs. So representing temperature upstairs. Let's go to the universal 2. Let's go temp down. So it reads temp up, temp down. So we got our upstairs temperature, our downstairs temperature, which makes kind of sense. Upstairs will be a little bit hotter. So for now, we will shut down or bring back up our wire sheet page. And on the wire sheet page, we have to start making sense of, well, I have two temperatures here. I'd like to see what's the average temperature in my house. So that average temperature in my house, I'd first go in down here, I'd minimize this, I'd go down to a math function, and I would say, alright, and you know, the path that we're taking is to pull you through a specific set of variables and components so that you can kind of get a feel and understand how they actually work. So let's just put add up here. Let's go output, add. See how I drag this fancy little wire down here, and I release it here. It will not, if I right click, I can delete it. But notice on the output, it will not take on the output. So if you can't figure out how to click, drag, and drop on input 1, we have a problem. You will have to talk to your IT department about that, because I'm not going to spend the time to show you how to drag this piece of wire. So get to work. Now, let's go to universal input temperature sensor 2 here. This input, this isn't registered yet. The channel type has not registered. Let's see if we can get it to register real quick. We might, or we might not be able to get this to register. Yeah, this will not register, and it will not populate when we change the type for now. If we exit out and come back in, it'll work. I think the new update will be fixing that. Refresh. So now we add these both together. So what happens? 78 plus 75 equals 153. Alright, now since we have 153, I would like to show you about the divide function. So we put the divide function in here, and I want to show you that I'm taking 153, I'm going into here, and I want to show you something that is actually very, very useful. So let's go down to types. Let's just say we have a constant float. Let's put a float in here. Now, the difference between a float and an integer is that you're going to be able to get a decimal out of one of these floats. which is very helpful. So this float value, we can change it here. Notice I'm up here. We can change it here, and I'm going to put a float in there at 2. If you're paying attention, obviously we're wiring this up to become a thermostat. But what I want you to see in this entire array here is that you can add stuff, you can divide stuff, and the float functionality is something that can help you overcome a hurdle maybe of a complex function for either like defrost timers or air handlers or other things, just to show you this is one application of the 1,000 you can do to actually make this thing, make a control strategy. Okay, so I kind of like this right now where we're sitting in here. Each one of these items, what you're doing is very clear. It's down to component levels. When you're teaching a course, you might want to keep the components down to 15 a page. Otherwise, if you see down here, you're going to be following this everywhere, and it just can get very, very difficult. You can zoom out about this far, you can zoom in this close, but we can start looking at this. You really need to understand that as the teacher, you're going to have to be able to organize those thoughts. And I know I keep bringing this up, but there's a reason. Okay, so we're going to go back up here and click on this tab like you would on your internet. See how you can kind of navigate through these up here. So I just click on these little guys, and I feel like Bob Ross again, all over. Okay, so we kind of handle our sensors that are coming in. The next thing we'll go into is, let's talk about control. So, organizing your thoughts and putting things together, it starts to help a lot if you drive the focus of labeling and paying attention to detail, so that when you're grading, organizing, trying to troubleshoot these wire sheets, it makes your life a lot easier. So, on control, under control, we're on universal inputs, so we got to go down to universal inputs. We've already used 1 and 2. Let's try to drop 1 down. Notice how 1 doesn't drop. Notice how 2 doesn't drop. Okay, it's not that the system's broken, it's that you're not paying attention. So look at this screen when I'm talking to you. And understand that universal input 3 is available. We will also take universal input 4, and we will square these suckers up. Maybe spread them out just a little bit more. Okay, so we have universal input 3 and 4, and these are going to be the push buttons on your thermostat. Okay, so we got these, and we have to figure out some type of functionality, and that functionality will be something that revolves around, like your regular thermostat. How do I get this thing to pulse up? How do I get it to pulse down? We have to create eventually a set point. So when we look at functions, I have inside of here a function of up down. Well, one of the things when you guys were getting into this originally is that on this up down, it counts a lot. It thinks too digitally out here, so push buttons going into it can be kind of tricky. I've talked with Contemporary, and they're working on this. I think Zach is reprogramming some of this so that it functions on either up or down, and it doesn't have to have an input. But in this case, I want you to understand that we're going to have to use the OR function. Okay, so let's go up to, or down to, let me remove the function. Let's go into logic. And let's take the OR function and drop that in here. And you know what? Let me show you both of these. If I highlight both of those, I can shift them on the wire sheet both together. So you drag, drop. You can move multiple blocks all at once. So they'll all pull at once. And it will reorganize your wire sheet. So on our output for our universal input, remember these are just saying UI4, UI3, UI4. Let's go first and change the names. We can change them in two places. Here, let's say this is UI3, up, that down. And we're taking the output of these, remember, and we're getting them from our emulator. And we're going to say these are not analog, these are going to be what? Binary. Okay, so binary, we're going to call this up. We're going to go in here and we're going to call this down. You also have to change it to a binary. Now, you do have pulse in here. You do have an analog input. That would be 0 to 10 volts. And pulse input will be something else. I'll see if I can do another video on some other functionality with these controllers, just to kind of give you a little bit more knowledge on this. Alright, submit. Up, down. Alright. So, I will change one of these values to 1. Just so when we go to the wire sheet here, you can actually see it. So we have 1, right? Our output. I'm just going to take the output of the binary right now. Output B for binary, and it's not considering it true right now because it's still calling it input 10 volt. So basically when we restart this in the emulator, this is one of the functions that will kind of mess with you a little bit, but if we log out and log back in, these will all change, and we'll do that before this is over. So we have two falses, false, false, equals false, but we'll use this on the input of it. And then if we want to count down, the reason we have to use this on a countdown over here is because to count down, you not only have to hit the down, but you have to pulse the input. But seeing as that we can only get one thing to go into each input, we can have multiple outputs, one thing into an input, we have to use an OR to stage these. It's like stepping it away, so this block or this block is allowed to pulse the input. That's why we use this, that's why we're going that way. So we want to next take this right here, this output. This is counting up or down. So when it counts up or down, when you go to pulse, we want a range of maybe 20 to 30. I mean, at most, we all know this is being built logically. Can we do this a million different ways? No. Yes. But what it's doing is showing you how to use up down, some OR gates, and how to use inputs to kind of create whatever control you're actually doing. So let's get an add in here. Let's go down to this math function over here, follow the pointer, look into the light, and bring this add 2 over here, and we're going to take this output and go into the input, and we're going to go back to our constant float again. Now, what this constant float is doing, you have to remember, this constant float is just giving us the ability to go in here and say, I'm starting at 50 degrees. Otherwise, your students are going to what? Students are going to be pulsing that thing for an hour, getting up, 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 up. And if you have a good starting ground at 50, right, and you add in like 30 or so, now you can move up or down. This will not go into the negative, this up down counter. I repeat, this will not go into the negative, if I'm not mistaken. But you're willing to prove me wrong, and if you do, well, I'm glad you're going to congratulate yourself. Okay, so one of the last pieces here that we need to minimize this, let's minimize our logic. Look, follow the pointer, and let's look at HVAC. And we have what's called a T-stat. Now, that T-stat is going to be in the outlet of all of this, and this 50-degree mark that we see here is going to be our set point. Okay, so this T-stat is an interesting block. Differential, what we're used to seeing here, that 2, our differential, if we go 2, I believe it gives us 2 up and 2 down. So it will turn off after 2 over, it will turn on 2 under. If I'm getting, actually I believe it's 1. It'll go 1 either way. So 2 is the whole of that dead band. So it will be 1 over or 1 under. It should start it with. If we wanted to create 4, I believe it's the same way. So you can play around with it and figure out exactly how it's put together with that, but more or less all it's doing is giving you the anticipator that you were really looking for. Okay. Now we have one thing on here, current value. So one of the things that's really important for us to know is, remember, sensors. If you can't go this way into sensors, let's just close these out to show you a way of these tabs on the top. And we're back in the sheets. Now we can reopen sensors again. We could also look under sheets here. Sensors, control, IO. Alright? And we have an output here, and right click on your block, it highlights in red. Go down to start connection. When you say start connection, you'll now go down to our control. Go over here and right click on the T-stat block and say complete connection. Now it's going to give you some blocks up here. These are some inputs that are available on that divide function. But what we're mainly concerned about is the out. And that out needs to go into what? The current value. It actually is kind of pointing in the right direction even in here. So we're going right into that current value. And now it's telling us we're at 76.5. So it's telling us the output is true. Okay? So if the current value, and why is that output telling us the value is true? Well, think about this in cooling. This is saying up here, is heating. Is heating currently is false, which means this would be in cooling. In cooling, is what? It closes the switch on what? It closes the switch on the rise, right? So since the current value is 76 and the set point's 50, it thinks it's way too hot in there and it wants to cool that space down. So unless its heating is changed, okay, this is going to have to, obviously, it's basically the output is going to be in cooling. So now notice the other one, lower. Lower is being used. Here's another way to use a binary output. You can use output, raise, or lower to basically wrap your mind around those same concepts. But if you understand how to just use the output, there is no difference really. So you'll see when we go into heating mode that raise closes and lowers will go false. Right? We got to mess with our set point here though. Okay, I can show you that in a minute. So let's go and start on our next section. I'm going to hold the control button and I'm going to roll my mouse middle roller back a little, or I can roll it forward, and that's how we're getting our zoom function to happen. Okay, so you can see very fast. Notice when I hit current value though, see how it highlights red here, or this guy? Notice when I hit this one, this little dot. Let's go back to sensors real quick. Notice that sensors, the output is red as well. It also tells you up here in the value where it goes, or where it's coming from and where it's going. So understand that component too, of how to trace wires down. You're trying to track the madness of students down, right? When you have a lot of wires on a screen and they're like flying all over the place, when you click on the wire you're looking for, like, man, where does this go? I mean, it could squiggle down through about 50 components. Depends on how much fun students were having the night before, right? While they were designing these sheets. So again, let's go back to sheets. And we have one left, this IO function. So if we go into the IO function, now we have just a basic sheet. We have 3 more switches. So we did universal input 3, we did universal input 4. Let's go up and grab ourselves some more IO. 3 and 4, so watch 3. 3 will not work here, 4 will not work here. I kind of like that function where it doesn't allow people to just keep stacking stuff. So 5, 6, and then 7. So what are these 3 that we're messing with here? These 3 here will be, if I click on 5, universal input 1, we could call this heat. Let's go to universal input 6. Cool. Let's go to universal input here and let's say fan. Okay. Now that we have our inputs, this will be from your switch box that you were given at the event. You have heating, cooling, and fan. If you notice, on every single thermostat in the world, there is heat, cool, and fan, right? And also, obviously a way to change your set point up, change your set point down. Now, fan's fairly simple. Fan would go out to obviously an output. So here's where we have our 3 inputs saying this has got to happen, and then now we want to also land, for first time here today, binary outputs. So we haven't used any outputs at all. Outputs are a little bit different as far as how they function within the context of this controller. They function a little bit differently because if somebody's commissioning $1 million piece of equipment, they want to make sure that you actually go in and enable these points. So this point, if you notice up here, when I go to click on this, you have to enable this point. That's so that if some crazy control strategy is in there, it doesn't start turning something on and destroying it, right? Eating it alive. So click in here, enable these 2 points, binary output 2 and binary output 3. Now, your controller, some people might think that, okay, well, we only have 6 outputs. Well, if you want more binary outputs, there are 4 analog outputs. If you set the voltages to 10, any 3 to 30 solid state relay will take 3 volts, and you can switch with just relays in between all of these. These can also switch relays that can turn motor starters on and bigger contactors and other things that will help control your situation and isolate, heavy duty power from the actual electronics and control. Remember, you always have to isolate your electronics and your control voltage from your power voltage. I mean, we do that in HVAC a lot with 24 volts and 480 or 240 volts in residential. But one of the things that we're not used to seeing is this the electronics isolation. And yeah, we can consider a board that, but when we're the ones designing the wiring, we have to also understand that we need to isolate the most expensive form of control, which is our controllers. Just throwing it out there. So, now, let's talk about heating. When in heating, right, this would click true. Let's go, so 5 is heating, 6 is cool, 7 is fan. Let's go into our sheet. 5 is heating. We're going to switch this to binary. Switch to binary. Let's go this to fan. Switch that to binary. Okay, so heating, cooling, and fan. Alright, so right now we are all set. Everything's still saying input 10 volts. When we restart the system, it'll repopulate correctly. We'll take the emulator down. We save this to the controller. It'll save the profile. This little guy right here, save to controller, is something that you want to be doing pretty often. But that little lightning bolt will save the controller. It also will save it to this emulator under how it's currently running. And one thing I want you to understand is that in heating, right, we want to go heating. What also has to be true? We want to say, well, let's go back down to basic logic, and we will go down to logic and to, I want to just throw a couple of these ands in here. We'll need the same thing over here in cooling. Alright, so when we're in heating, this output binary is going to be true, right? So I need that true, and what else do I need to be true? I need there to be a call no matter what from our thermostat. So if I go to the thermostat and I look at the output, right, I could say start connection, go back to I/O, I'll say complete connection, and it's asking me where output. I want the output to go to the input of the AND. Why? Because I need it to be calling, right, for heat, and I need to be in heat. So there's really no other interlock that we need technically when we go into that. So our input here is still false. Here's the thing that we're missing though, is that if we look back on a control, is heating is false. So what I want you to do is understand that when that heating becomes true, we say start connection, and I want this to go into control, and I want a complete connection from heat, and I want it to come out of the output of the binary, and I want it to go is heating. Okay, now see is heating here where it says false. Let's go and see. Maybe I have to restart the controller, but we'll see here in a minute. 1. And our I/O will not do it because it's not there. Our binary is still saying false because the input is 10 volts. So that's okay. That's going to get fixed when we log out of this controller and log back in. All of the changes that we've adapted within the emulator on that web page screen are all gonna reset with the right properties, and when this turns on, I bet if we just went save the controller and we just said close and we opened it back up, let's see if this works. If not, we'll do a full reset. We're under sheets. Should be I/O. And yeah, it didn't reset, so it's okay on the emulator. Let's finish our logic so we don't have to redo this again and again. So now the only time you see this little guy here, that is the little connection that is going to, let's go into control, that goes to this is heating right here. Okay, when I go back to I/O, you'll see it lit up, and this is lit up because it is going to say, hey, when I'm in heating, which is physically being thrown when you turn the switch into heating mode, it's going to put a 1 on that thermostat and say, okay, now it's on a rise. Alright, another thing, let's talk about cooling. Output binary on cooling. Let's go, if it's in cooling, oops, it always lets you know when it calls you a dummy. It says, hey, you went to the wrong spot. Pay attention. Pay attention. Let's go to control now. Let's see if we can say start connection. And let's go complete connection. And I want the out to go to input 2. So notice how that's true. Right now we would actually be calling for cooling if we had the binary functionality set and we said this was actually true. So there we are, and our fan is just a simple switch, right? Fan is either on or auto. Actually, when you go to hook this up to any furnace in your lab, your board is going to control the fan just because of the combustion and ANSI standards within the electronic control strategy of that actual board. So you do not have to worry about that. Output binary. When that fan switch goes, it turns and pulses 24 volts to the green, right, on your actual furnace terminal board. So what we have here is we got our control, we got our I/O. Let's go down this tree a little bit. We've seen how to develop and design a couple of different things here. Let's look at sensors. We have sensors in here, and what I would like you to see is maybe one other function. And bear with me, this is off the beaten path just a bit because we didn't have enough time during the last event, but this constant float at 50, let's change things a bit. Right click, delete this, and let me show you one other function that we can be doing. Look at CC Controls BAS 22 I/O. I would like you to grab a VT01, and what this is, it's a virtual point, and that virtual point is programmable, and we can put a float value in there. So if we look at this, be like, let's just call this set point. Too many words? Yeah. Set PT. Okay. Now, that float value, we can go ahead and change a different way. Let's go into our emulated screen, and as we sit in here, here's what I didn't get a chance to show you. There's a thing called virtual points. Follow the arrow, follow the arrow, follow the arrow to virtual points. Now, you see how this is green? It's actually on the actual page. So click on virtual point, and now we're sitting on this virtual point. Default value, I'm going to say 50. And it says write to wire sheet or read from wire sheet. You can actually flip this back and forth. So why is this important? Well, if you want to read an analog value of how something's reacting, like a temperature of a freezer or a furnace, while you're sitting in the classroom and you're looking at this web page and controlling this from afar, a virtual point is a great way to see stuff inside of this program or control something. So when we go to look at this, you see virtual point. Now, we're writing to a web page, but if I was reading from a web page, this is virtual point 1. Let me call this something set point. This is set points. If I was reading, I could see return temperature on a furnace. I could use this one as a supply temperature on a furnace. So I could be watching this in real time. Auto refresh would be on. Remember I said operating, auto refresh could be on, and you could actually sit there and watch and analyze and talk with your class about these set points and say, hey, what's actually happening in this scenario? Look at how this is heating up. Gives you a different way to learn and try to understand what's happening, with whatever system or control strategy you're running. I'm going to close this out. I'm going to go to my controller. So again, the virtual point is very useful, I think, from an education perspective on how you can get students to interface with all of this. Now, don't get me wrong, wiring and what you'll be doing, it's, wiring to universal input, you have to physically wire it, and do not forget the common point. If your controller wires and stuff are all going green and things are messing up, you pretty much got the common wrong. So remember, the common does not mean neutral. The common does not mean neutral. And one more time, if you look at this screen when I'm talking to you to pay attention to what I'm telling you, the common is not neutral. Okay? So it's how all digital commons, relays, all other functions of switching actually operates. So you have to pay careful attention to the way in which you wire something. Just one not wired correctly can wreck all of them. So I'm going to save this to the controller. App was saved successfully. And I am going to close this down. I'm going to shut this down, shut this down, and I want to kill the emulator. Now, let's go back into it. Again, you're on BAS 20 right now. I would like you to be on this 312722 because that is how we saved it within the emulator. So now we start this emulator. Okay, temp up, down, heating, cooling. There we are. Our virtual point should be in here. Set point. There we are. Minimize that. Let's open Sedona. And we can either open the connection here, and this time we're going to open it here. Our 127001, that's our emulator address that we want to go with. And type in the top secret password of ADMIN. Hit OK. There is a lot to learn here, but if you just keep your head on straight and you understand the fundamentals, I think you got a great chance at just, you know, understanding how all of this works. And you don't have to be complicated. Don't overcomplicate stuff in the classroom. I don't know how many times I'm going to tell you this, you know, over the tenure and over the time that we have a relationship, you know, as a group, is that if you overcomplicate controls, it is just going to limit what you can do. The simplest version is the best. Interlocks are great, but just remember, use AND circuits, use logic. You know, this is a great way to teach digital logic, ORs and ANDs and NANDs and NORs. Start to really experience it with the students. Do it at the same time. If you want to become this all-knowing person, this is all a learning process with all of us, and it's always going to keep evolving. So, you know, introducing somebody that might be the next controls guru of the world, you know, to something, you know, everybody's going to have a different level. Just, you know, keep your head on straight, move forward, and have a good time while they're actually drawing up these control strategies. And if you don't understand, you don't understand. So, notice, everything's looking good now. We have output binary true. Now the trues and the falses are working. So see how that was 1, it became true, 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 and the false is not working correctly. Why? Because our temperature, right? Let's go back to our, I like going 2 different ways just to mess with you. I had a friend in Cincinnati, when I had lived out there for a couple years, he used to drive to places 2 different ways because it's around hills everywhere you go. So he used to love messing with me. So I think it helps you develop an aptitude. Remember to zoom out, hold the control button down, and roll your mouse button back. And notice 50 degrees. So where are we at here right now? Currently our output's 51 degrees. Well, if the current value is 76 and our set point's 51, we're never going to be calling for heat, right? So we have to change the set point here. Well, let's go to our emulator. go to our emulator, into our virtual point, and this is what I was talking about in the classroom. You can go in here and say, there we go. Let's go back to our wire sheet. 80, 80 is heating. Current value is true now. So our set point's 81, our current value is 76, so it's turning the heating on. Let's go back into our I/O. Current heating's on. It's going in. We're true, true. Remember the is heating function right here? The is heating is also being pulsed at that same time with a true. That's why if we go into control, we see is heating is true, and our output's true. If this was not enabled, right? Gets a little tricky sometimes, so you just gotta click it to death. If I don't have that point enabled, remember, outputs have to be enabled so we don't destroy equipment. Remember that for your lab when a student's about to fire something up and it starts sounding like, you know, a motor's screaming for the last bit of its life as it pulls locked rotor amp 25 times in a row. Just remember, keep that in mind. Enabling points is a good function. It's not annoying, it's a good function for commissioning. But with that being said, I hope everybody had a good experience here. If you have questions or other concerns, just talk to the BAS Center, and you know, send me an email, and we can work on this together, because that's the only way any of this is ever going to get done. You guys have a good night, and we'll talk soon with more control strategies. This is Bob Clark signing off.